Now, in the previous example, we saw error, this hashable error. And now that we're talking about things like tuples and as dictionary keys or dictionaries, maybe we should talk about hashability. What makes something hashable? And it's a very easy question because we know, well, if it's a none type, it can be put into a dictionary. It's definitely hashable. If it's a numeric type, it can be put into a dictionary. It's definitely hashable. If it's a textual type, a string or a byte string, definitely hashable. If it's one of these two container types, the tuple or the frozen set, it's definitely hashable. And if it's a list, not hashable. If it's a set, not hashable. If it's a dictionary, not hashable. And from this, we could say something like, well, it's pretty clear that for these built-in types, if those built-in types are immutable, they're hashable. If those built-in types are not immutable, if they're mutable, they're not hashable. And for the pattern that I've shown you here, this is absolutely correct because textual types, they're all immutable. The numeric types, they're all immutable. These two container types, definitely the frozen set's immutable. It has it in its name, frozen. And the tuple type, as we know, is immutable, even if that's not the most interesting thing about the tuple type. And these three types are definitely mutable. But where people get this wrong, and they get this wrong very, very commonly, is hashability does not imply immutability. In fact, there is a strong relationship between hashability and immutability, but it is not the case that one implies the other. And I'll prove it to you right here and right now because a slice object in Python is immutable, but it is not hashable. You cannot hash slice objects. And the reason you can't hash them is because that would create an ambiguity between, think about this, this is great. Everything ties together. If you had a dictionary like this, and you wanted to do some sort of slice-based indexing like you commonly do in pandas with like a dot lock or something, here, this is going to turn into a slice object. Well, if you could put a slice object as an entry in a dictionary, then there would be an ambiguity here between, well, did you mean to look up the slice object or do you mean to do some sort of sliced indexing? Again, we have this common problem where we have two completely separate notions in the same channel. This is an out-of-band, in-band ambiguity problem that we have again. But that's why that is. And that might be considered a little bit of a corner case, but still, the point stands. Slices are immutable, but they're not hashable. And so we can see that one doesn't guarantee the other. Here, I have a custom object. And my custom object is mutable. It's a data class, but it's not hashable. But it is hashable. And so we can see some mutable things can be hashable, some immutable things are not hashable. And you might say, okay, that's also a kind of a corner case because it's your own custom object and you can do any kind of crazy, stupid thing you want with your own custom object. But here, I have a generator expression. And a generator expression is definitely mutable because it can be consumed. So every time you look at this thing, if you pull a value out, well, the thing changes in terms of the values that it stores. But generator expressions are hashable despite being mutable. So even the built-in types include examples where immutability might not imply hashability, and mutability might not imply non-hashability. Let's break this down and try and understand what makes something hashable and what's the relationship with mutability or immutability. And let's go back to my custom object and think about how I would compute the hash for that custom object. I roughly have two choices. I can either compute this hash by value or by object, by equality or by identity. Here's what I mean. Here's my data class with two elements of data, A and B, that default to 0 each. I can compute the hash by the value of this thing, by the A value and the B value. So the hash is just determined in terms of this tuple that I've constructed of the A and the B value. Fine. If I do that, and this thing is, remember, this thing is mutable, what I could see in my program is I put an object into a dictionary, I mutate the object, and then taking the exact same object, I try and look it back up out of the dictionary, and it can't be found anymore. Because if I'm hashing on the value, if I'm hashing on the equality, well, the object after the mutation no longer equals what it was before, and so it's gotten lost. And so hashing based off value or equality won't work if we are worried about losing things in the dictionary, and we can clearly easily lose things in the dictionary. So that doesn't work. Let's try hashing by object, hashing by identity. So I'll compute the hash by taking the identity of the object, the unique identifier for the object, and we'll see if a problem arises. Well, what would happen in that case is I put this object into my dictionary, And many thousands of lines later, I want to pull this thing out. And the way I pull this thing out is I construct another T object. Because there's no guarantee that at point A of my program, when I have the original T object, and point B of my program, which could be thousands of lines later or a different module, or many minutes or hours later, after the garbage collector's already come in and deallocated the original, well, actually, the dictionary would hold a reference, so it couldn't deallocate that, but you get the idea. I can't look this up. I've kind of lost this object because I can't get it back out by its equivalent value. This would be like if you had a dictionary and you put the number 0 in it, and then later on, you couldn't just say D of 0. You had to find this exact 0 object that existed here. Now, of course, small integers are interned, but if this were maybe a larger integer like 100,000, the point still stands. You'd have to find not the 100,000 value, but the actual 100,000 object that you used before. And that would be very clumsy. So you're at risk of losing this thing in the object again. But it turns out that this is not an unusual thing to do. When you have a mutable object, it is reasonable to compute the hash of that mutable object. You compute it off of the identity. Because this style of losing things is meaningfully different than the previous style. What you lost was the ability to retrieve something, but you didn't ask the dictionary for something that you already put in with the exact same object and said, oh, never heard of that before. You just lost the ability to randomly reconstruct that key and then pull something out later. But what if you never randomly reconstruct the key? What if you use this dictionary as not a random access, a disintermediated access structure where you're just reconstructing values and then looking them up out of the dictionary? You're instead always referring to the same underlying object because you let the structure, you let the container tell you what it contains, and you never randomly pull something out of it. I'll show you what I mean. This comes up all the time when you're using Network X, because a Network X digraph may want to have custom nodes, and those custom nodes could be anything, including Network X digraphs or custom objects. And those things might very well be mutable because of course they might be mutable. This might be very useful for our analysis. Maybe we're doing some graph analysis and we want to tweak something and run something over the graph and then tweak something again and run something over the graph. And Network X makes it very difficult for you to do copy on write or to do any sort of really efficient copying. And so you probably want to just make this mutable. Well, if I were to hash this mutable object on its identity, it would actually work out okay. Because in practice with the Network X digraph, usually I'm not saying, oh, just give me this node. I'm usually doing something like iterating over the nodes by asking the container what it contains, or I'm storing exact object references to these entities somewhere off to the side, like here, and then doing something like a breadth first search or a depth first search from the root. And think about it, with the Network X digraph, how do you know what the root entity is? You have to store that off somewhere. You're going to store the exact object. Well, it's okay. This thing's not going to get lost because you're not ever doing this kind of disintermediated access to the underlying mapping. You're always being intermediated either by some local storage here or by the type itself, either asking the type itself, tell me what you contain, or storing something off to the side and then looking that up. And you can think about, if you were to use a Network X digraph in this case, it may be very much the case that you want to be able to look up elements by value. What you'd probably do is you'd probably have a value mapping, like a node names mapping, comes up all the time, and you'd have a mapping between each node's name or identifier to the actual node object itself. And this is what you would use for putting things into the digraph itself and for identifying which the root one is. This is how we get the root one. And very likely, instead of doing these as like standalone variables, what you'd probably do is you'd probably subclass a Network X digraph, and you'd have methods like class network subclassing this, and you'd say something like find by name, and this would do something like, at the most naive, for n in g.nodes, if n.name equals name, return n. Otherwise, because we want this to be unambiguous, raise a key error, or maybe an index error. And here you give it a name. This is likely what you'd do. And this is the the most naive approach. And then later what you would do is you'd probably, on the construction of this thing and on any mutations of this thing, what you would probably do is then cache this in some internal dictionary that maps these elements. You'd have to be a little bit careful about mutations because you have to be able to remove things and whatnot, but you do some sort of caching for this. This is what I mean by intermediated access. Why does this matter? Well, this is something that it actually requires a little bit of deeper thought to really see why the idea of hashability and immutability and their interrelation matters. And it comes to a larger topic that's come up quite a bit in these sessions. If you joined us for the Precision Python session, where we put together a simulator for a distributed algorithm, the last variation of that simulator had a property that I called value disintermediation. It was object-oriented. It was truly object-oriented. Not in the sense that it was objects with data and methods, but it was that there was no dictionaries that map the name of something to some Python object. It was a distributed algorithm, and it had different node types like proposers and acceptors and whatnot. And those different node types were modeled as classes. So there was a class for the proposer and a class for the acceptor. And there was a class for, say, the learner. And when I had the nodes, I didn't do something like, oh, nodes equals proposer mapped to some objects. I did nodes equals the proposer class mapped to the actual underlying objects. In this case, these were asynchronous methods defined on instances of these classes. And there was none of this intermediation where you had values that you would look up things up into over here and there and then kind of map things through. And I suggest that this is a very contemporary Python style because what you're really leaning into here is the idea that the garbage collector is managing the lifetime of these objects, and it's doing a better job of managing the organization of those objects in the lifetime than you are yourself. And as a consequence of that, rather than have these intermediaries that use values to map the underlying Python objects you want to work with and how you access them, you just pass those things around. Well, in order to pass those things around, you want to be able to put them into sets, you want to put them into dictionaries, and they need to be hashable. And you need to understand that it's reasonable to hash these things by identity if you don't need disintermediated access, if you're always just saying, oh, take this dictionary and iterate through the key value pairs. I'm never actually randomly accessing a value given the key. This is also why you often see that I'll use the enum. It's not because I love enum types from languages like C or C++. It's because what the enum does is it allows you to have at the boundaries of your program values like human-entered A, B, C choices to map them into the object model, to map them into these unique singleton choices objects, and then everywhere else to say not if choice equals A, which is a string comparison that could be slow, but if choice is this singleton object, which is a faster comparison because it's a direct pointer comparison, and also eliminates one additional unnecessary intermediary. That's a big benefit to the clarity and the structure of my program. And in general, what you can see is in many of your programs, you have things like data, and there's some identifier, metadata, and some identifier, and some entities. And these ellipses here are the actual underlying Python objects you're working on. And you can imagine in this case, you're basically saying, take this string identifier and map it through this and to this. Well, that's really not a good idea, because if one of these things needs to be garbage collected, well, it's going to linger in the rest of these. You're going to have a lot of additional sophistication to make sure that once the entity with identity 1 is no longer in use, you clear it out from data metadata. And sure, you can use a weak value dictionary or a weak key dictionary, but why not just let the Python garbage collector determine the lifetime of all of these things? Why not just not have these intermediate values? Why not have values, namely strings and identifiers and things like that, just be something that you look up when you need to look it up, but not be the key to how you structurally arrange your program, and instead structurally arrange your program by just passing rich objects around? This is the approach. Now, there's another consequence of this approach, which is this also motivates why we want to use async I/O, because in the object-oriented, value disintermediate approach, you can no longer use multiprocessing. Because multiprocessing requires that you be able to pickle things as you move them between processes. And in the object approach, well, you're not guaranteed to be able to pickle any arbitrary object. We can't go into why you can't pickle arbitrary objects, but it's an interesting question, which we may talk about later. But What this then leads to is why you might want to use something like async IO or over multiprocessing or threading. And one of the reasons for that is the arbitrary ability to work within the same process with the same objects and have the same garbage collector managing the lifetime of those without these intermediaries. And it all comes down to understanding how these lookups might work and understanding that it's appropriate to hash these things on identity if you add that additional qualification of no longer needing random access / this intermediate access.